Sarah, can you hear me? I'm speaking now.
Yeah, good hockey question there, Jim.
One of my Michigan Tech PhD students. Hi, Mark. Good to hear from you.
Rajendra, there'll be a recording. And we'll also have our email addresses on the last slide in case people want to contact us afterwards. They're PDH, I guess. Those are going to be those certificates, right?
Yeah.
Some people are saying there's no sound over the computer, but only over the phone. I don't know why that would be.
Hi, Pablo.
If you click on, if there's no sound on the computer, just use your cell phone separately. And if you click on the phone icon on the top left, it's in the center, but it's towards the left, that's the phone number to use. Okay, we're going to go ahead and get started. It's 12:03. Good morning, everyone. This is Marissa Waterman. We're so happy to be doing this webinar today. The title is Low Cost Biofilters for On-Site Wastewater Nitrogen Removal. Today we're honored to have three speakers. First up is Damon Anderson. He's the Vice President with Hazen and Sawyer. He has over 40 years experience in wastewater and wastewater treatment and water quality. He's been a leader in research on on-site wastewater treatment systems and their impact on water quality for over 3 decades. He was the project manager for the Florida Department of Health's on-site sewage nitrogen reduction strategies study, which won the 2016 Grant Award for Engineering Excellence for the Florida Institute of Consulting Engineers and the 2016 National Honor Award for Engineering Excellence from the American Council of Engineering Companies. He's also authored over 50 publications which have appeared in technical journals, engineering manuals, and conference proceedings nationwide. Our second speaker today is Serena Argas, and she is a professor of civil and environmental engineering at the University of South Florida. She holds a BS in environmental engineering, and her research interests are centered on environmental biological processes, including biological nutrient removal and waste-to-energy technology. Our third speaker today is Dr. James Mihalich. I hope I'm saying that right. He is a professor of civil and environmental engineering, and he has, and he's also the director of the Center for Reinventing Aging Infrastructure, Nutrient Management, and director of the International Development Engineering Program at the University of South Florida. He's a board-certified environmental engineering member and past board trustee with the American Academy, and also a fellow with WEF and AEESP. He's also authored close to 200 written materials and is lead author for 4 engineering textbooks. So we're going to get started. Damon, you're first up. You can go ahead whenever you're ready. And we'll also open up for questions at the end, so you can text your question in the attendee chat at the end, and the 3 speakers will just go through and answer the questions at their own pace. And that's it. So everybody, here's Damon.
Okay, thanks, Marissa. I appreciate that. Good afternoon or good morning, I guess, depending on where you are. We are pleased to be able to present our work to you today on this webinar. This project consisted of a multifaceted team of university, local, utility, and private consultant personnel, and resulted in a really interesting project that built upon ongoing Florida Department of Health work. And we'll go through that as well. Next slide shows an overview of their presentation. I'm going to go through some intro material and some recent DOH work that USF then built upon, and then I'll turn it over to Serena and Jim to discuss their university research and a few other items. Next, I'd very briefly like to go over some nitrogen impacts to water quality. I want to keep this brief because I know most of you are probably familiar with this area. And the next slide shows that there's like two major areas of concern we have primarily for nitrogen loading. And one is public health, where we, of course, have a Safe Drinking Water Act standard for nitrate. We have harmful algal bloom concerns in areas that use surface waters for drinking water. And then, of course, the second major area is ecosystem health, and that area is probably receiving the most attention, or at least a lot of attention right now. And that's because nitrogen is a limiting nutrient in many water bodies, which can result in algal blooms, loss of habitat, hypoxia, fish kills. And these kind of things have been documented in many places in the country, but most notably Cape Cod, Long Island Sound, Chesapeake Bay, Puget Sound. Here in Florida, we have problems in Tampa Bay, Sarasota Bay, on the East Coast, the Indian River Lagoon, the Florida Keys, and then specifically our freshwater springs and many other places are impacted by excess nitrogen loading. So in Florida, one of the primary concerns, of course, is our freshwater springs. We have a large network of very large freshwater springs. This slide shows Itchituckney Springs back in 1995 when we had crystal clear water and brilliant submerged aquatic vegetation. Followed on the right by that same spring, same location in 2012, where you can see the vegetation has been reduced to nothing but algae and the water has become pretty murky. The next slide shows some estuarine problems we also have here in the state. In fact, there's been several of our estuaries where states of emergency have been declared because of harmful algal blooms overwhelming the habitat of the estuary. We also have red tide, which is a natural occurring algal bloom, but excess nitrogen seems to exacerbate that red tide problem. So there are many, next slide, there are many sources of nitrogen to water bodies, but today we're going to talk about the impacts from conventional on-site wastewater treatment systems. Now these systems are low cost for suburban and rural areas. They're very popular. They have low chemical energy use, and they provide really good treatment performance if standards are met in terms of their installation and and operation for things like BOD, total suspended solid, fecal indicator bacteria. And they provide groundwater recharge, which is a positive impact from these systems in some places. And also, you might say some on-site reuse in some applications. Problems, though, are that they have only limited nitrogen reduction. If there's a 2-foot unsaturated soil below the drain field, which is the place where the effluent is released, we can get 20 to 30% nitrogen reduction, but not too much more than that, unless there are some very specific soils that might do better. Another problem is lack of operation and maintenance. These systems are typically not operated and maintained except by the homeowner. There's no organized system of operation and maintenance in most places. So that can be a problem. And then thirdly, there's variable loads and long idle periods from certain applications in tourist areas and some residences where both people work, what have you. Next slide shows that these are, there's not an isolated thing on-site wastewater treatment systems. Nationwide, about 23%, or almost a quarter of our homes utilize on-site systems for their wastewater disposal. Some states, as you can see, have greater than 26% of their homes served by on-site. And several states, I think there's about 10 there, that are greater than 40% of the home inventory is served by on-site wastewater treatment systems. So they're not unusual. They're quite numerous in the country. Of course, the impacts from on-site systems from nitrogen are very site-specific because they use the soil and the groundwater as their receiving body. So some watersheds on-site end loads are relatively low. Here's the Chesapeake Bay nitrogen loading model where they estimate only 5% of the load to Chesapeake Bay is from septic systems or on-site systems. Next slide shows a similar chart for the Wekiva Springs study area in Florida. This is an area near Orlando where the on-site wastewater treatment nitrogen loads are estimated to be relatively high. Here on the section labeled OSTDS, about 26% of the load has been attributed to on-site systems. And then there's specific, smaller maybe specific watersheds where on-site systems can be very high as part of the nitrogen load. Here's the Kings Bay, Florida spring shed, which is in the Crystal River area, where on-site systems are estimated to be about 53% of the load, which is a high percentage of the nitrogen load to that water body. So next, I want to talk about work that we've been doing on nitrogen-reducing biofilters. And I'm going to start by talking about Florida Department of Health studies that we conducted and lessons learned that then led to the work and kind of coordinated with the work that USF was doing on the project they'll talk about. So next slide talks about the nitrogen reduction studies in Florida. In 2008, the legislature here directed the health department to conduct a study to further develop cost-effective nitrogen reduction strategies for on-site wastewater treatment systems. And this was due to these crises I showed you, the springs impacts, the estuary impacts. And they wanted systems, the legislature wanted systems that were similar to conventional on-site systems in terms of their operation and maintenance, and thus relatively passive in operation. And this resulted in the Florida On-Site Sewage Nitrogen Reduction Strategies Project, which began in 2009. And the next slide shows 4 major areas that were included in this study. I was the project manager for this study with DOH, for DOH. And today we're going to talk mostly about task A and B, which were the treatment performance aspects, the treatment technology aspects of the study. We also did a lot of groundwater work. There's a lot of results from this study. There's many, many pages of documents, and you can see more results on that FDOH website at the bottom of the slide, where all the deliverables are listed and shown. But today I'm going to talk mostly about the treatment performance aspects and the systems we developed, and even then, just a few options that we came up with. So next slide defines what we mean by passive nitrogen reduction system, which was a term given to this study and given to these systems. And again, kind of a repeat, but they're really defined as nitrogen removing on-site systems that are as similar as possible to conventional on-site systems in terms of their operation and maintenance. Now in Florida, we developed a specific definition that could be used more applied to code language and what have you. But that specific definition is on-site nitrogen reduction systems that reduce effluent nitrogen using reactive media for denitrification and a single liquid pump if necessary. And this pump provision was put in there because many of you, if you know Florida, it's very flat in most places. Our topography wouldn't allow for much additional treatment process to be added to the system if you couldn't raise the liquid up. So we added this single liquid pump if necessary. So we looked at, in terms of passive media, we looked at nitrification media such as sand, expanded clay. We looked at cleanup tile as well. But these are medias that could be layered in an unsaturated way and effluent percolate through them for nitrification. For denitrification, we looked at 2 types of media, lignocellulosic-based material, wood-based materials such as wood chips, sawdust, what have you. And then also, and that provides an organic supplement for denitrification. And we also looked at an inorganic supplement in the terms of elemental sulfur for denitrification media, which uses more of an autotrophic process for denitrification. We looked at both of those. Next slide shows what we mean by nitrogen reducing biofilters. The simplest concept we came up with are these in-ground layered on-site systems that reduce effluent nitrogen using reactive media for denitrification in a relatively passive process. So the arrow there on the left shows this 2-stage biofiltration process. You simply build kind of a septic system drain field type process where the upper layer is sand or some nitrifying media where we nitrify compounds to NO3. And then the second stage, which underlays that media, is a second layer of media which is used to denitrify the nitrate to nitrogen gas. And again, the denitrification media we looked at were lignocellulosics and elemental sulfur. The next slide shows a successful prototype we developed. We did a lot of bench scale and lab scale work initially, but then we actually built a one-third scale in-ground nitrogen-reducing biofilter at a site here near Tampa. The site was high groundwater, so it required a mounded system. But essentially, we built a mounded system that took effluent from a septic tank, applied it via drip irrigation to a sand mound that included about 18 inches of sand, underlain by an HDPE liner. You can see their V-shaped liner, which was filled with a mixture of sand and sawdust. So that effluent would percolate through the upper layer of sand, be nitrified, and then saturate in that liner. So denitrification could occur using the lignocellulosic material as an organic carbon supplement. The effluent from that liner, then we did this in a modular fashion so we could look at both methods. The effluent from that liner then went through an upflow sulfur tank. Simply elemental sulfur with a perforated pipe at the bottom, so effluent from the liner flowed up through the sulfur, and then we just disposed of it out through infiltration chambers in the ground. So this was very successful in terms of its performance. We achieved 90% total nitrogen reduction off that liner, in other words, through the lignocellulosic sand media, and then a total nitrogen reduction of 95% through the ultimate system after the sulfur tank. Very, very good performance, and led us to the next slide where we actually implemented this at full scale then at a single-family home in Florida. Again, very similar concept. We built this in-ground nitrogen-reducing biofilter. At this site, we actually used the effluent for on-site reuse to irrigate the very nice landscape this homeowner had at his house. It gives you some of the characteristics. It was, again, a mounded system because of groundwater elevation concerns, which we do have a lot of in Florida. Next slide shows the schematic of the system, or at least a cutaway of it. And again, this was very similar to the prototype I just showed you. It was a lined system, which included a sand layer underlain by a wood sand mixture, effluent applied by drip irrigation. That's the purple pipe. The effluent then flows out of that liner into this sulfur tank, which also served as a storage tank for irrigation. It upflowed through sulfur, which was in that tank, and then we took off of that and used it for drip irrigation in the landscape area you see there around the house and along that fence. So again, nitrogen removal and on-site reuse for the effluent. Next slide shows the results of this system in terms of the monitoring. I'm just really going to talk about the nitrogen results today. The septic tank effluent we applied was about 50.5 milligrams per liter total nitrogen. After the 18 inches of sand layer, it was reduced to about 50% of that, 50% reduction through the first sand layer. And then once it got into the liner and went through the lignocellulosic sand mixture, the effluent coming off the liner was about an 84% reduction in total nitrogen. Then it went up through the sulfur tank, and total effluent reduction then was 96% total nitrogen reduction from the system. And interesting also is that we only had 5 fecals per 100 mils, five fecal counts per 100 mils in that effluent as well. And the concentration there that we were using for irrigation was 1.9 milligrams nitrogen per liter, reduced from that 50.5. So very, very good performance, very high level of treatment. Next slide talks about the operation and maintenance of the system. It was very effective in terms of operation and maintenance. It was simple. Used about 1 kilowatt hour a day, which came to $3 to $4 per month in electrical use for the homeowner. That previous slide showed was 500 days of after 500 days of operation. During that period, we saw no biomatter clogging of the infiltrative surface. We saw no measurable reduction in volume of the sulfur media in the tank. And I add that we're not doing it, but DOH continues to monitor this, and the performance is still very good after over 5 years of operation of the system. The next slide. Of course, with these kind of improvements in effluent quality, you would expect groundwater quality improvements. And we've experienced some very interesting groundwater quality improvements. The next slide shows 2 plan views of the site. The one on the left is these are plan views of the nitrogen plume down gradient from, on the left, the existing drain field before the nitrogen reducing biofilter was installed, and on the right, the new system after the nitrogen reducing biofilters were installed. And you can see the middle scale there. The colors represent total nitrogen concentration in groundwater from 0 up to greater than 40 milligrams per liter. You can see on the left there we had quite a nitrogen plume down gradient of this existing drain field. The darkest orange was somewhere 40 milligrams per liter or above. After the NRB installation, you can see we were at background levels everywhere down gradient, pretty much of the new system. And that occurred relatively quickly, 2 or 3 months. And this picture here is really a snapshot in time. But if you look at the next slide, we'll see that although that was a snapshot, the results were consistent after the installation. This is a time series plot of total nitrogen in groundwater at one of the most impacted wells. It's one of the wells in that dark orange area. And you can see prior to the installation, left of the dash line, relatively high concentrations fluctuating due to precipitation and what have you, but relatively high concentrations. And then on the right, consistently low concentrations after the NRB was installed. So we essentially pretty much remediated that groundwater on site by installation of this system, which was very, very interesting results and very promising. The next slide then shows that for early implementation in the state, we have focused on development of a very simple layered system that is now in the code in the state of Florida, where there's additional modifications being talked about, additional process configurations being talked about for the code. But right now, we've just focused on this very simple system, the layered drain field, which we call the nitrogen-reducing biofilter, in-ground nitrogen-reducing biofilter. And again, you have septic tank effluent distribution above a sand layer where you get nitrification, underlain by a denitrification layer, which we're recommending a roughly 50-50 mixture of sand and either sawdust or wood chips or some lignocellulosic material, and then underlain by a liner or some lower permeability layer that can allow moisture content increases in that lower layer for denitrification. These are being implemented in the state of Florida and elsewhere. The next slide shows a nicer schematic of the system. This was actually a schematic of what we're doing up in Long Island right now, working with Stony Brook University. Again, household discharges into a septic tank effluent goes to a pump tank goes to this nitrogen-reducing biofilter. Picture on the left shows a low-profile distribution system we're using in some of the systems in Long Island to raise the system up in the soil profile. And then it's, again, underlain by an unsaturated media such as sand for nitrification and a lignocellulosic sand mixture for denitrification below that. And again, these are achieving good results in Cape Cod, in Long Island, and in Florida as well. So that's being implemented. It's in the Florida code and being implemented in other places as well. With that, I'm going to turn it over to Serena, who's going to talk about what USF did in moving forward with some of this work and some really interesting research that was done at the university. Thank you.
Okay, thanks, Damon. So we were very honored to receive the AAEES E3S award in the university research category for this project. So I'll tell you a little bit about our process, hybrid adsorption biological treatment systems. One of my students, Laura Rodriguez Gonzalez, came up with this acronym, HABITS, for this process. This is really just reviewing what Damon just talked about, showing the home, wastewater going into the septic system, into the septic tanks, and then followed by a unsaturated nitrification reactor, and then a saturated denitrification reactor containing a reactive media, and then finally to the drain field. Just a little review of biological treatment processes here. We have our influent wastewater that's high in organic carbon, measured as COD, organic nitrogen, and ammonia. That goes into the septic tank where you get some ammonification occurring coming out of the septic tank. That ammonia goes into the aerobic biofilter. where nitrification occurs. So ammonia is being converted to nitrate by nitrifying nitrifying bacteria. If we have a recirculation line, we can take the effluent or portion of the effluent and recirculate it back to the septic tank or a pre-denitrification tank where we can get some denitrification occurring. I don't know if you could see my pointer there. After nitrification, then we go to the saturated anoxic biofilter containing that solid substrate that becomes a slow release source of electron donor for denitrification or the conversion of nitrate to nitrogen gas. And as Damon mentioned, they worked with sulfur and wood chips. We also looked at the combination of sulfur and tire chips. And then we saw in Damon's study the very high quality of the treated effluent. So I'm going to talk a little bit about sulfur oxidizing denitrification. I saw in the chat there were a couple of questions coming in about that also. These microorganisms are chemolithotrophic bacteria, which means that they use an inorganic compound, in this case elemental sulfur, as their energy source. And they're autotrophs, and they use carbon dioxide as their carbon source. And they use nitrate as their electron acceptor. Some of the advantages of sulfur oxidizing denitrification is that these organisms grow very slowly. They have low biomass yields. And so that means we get less clogging in the reactor. So we have less backwashing needed, less operations and maintenance costs. The sulfur pellets themselves are a byproduct of petroleum refining. And so it's a very inexpensive substrate to use for denitrification. Another a disadvantage of this process, though, is that you do get some sulfuric acid production, so some acidity. And so we found in our research that crushed oyster shells, which are another waste byproduct, was a very effective buffer. It's 95% calcium carbonate. It actually provides a good material for bacteria to attach to. And so we found that adding the oyster shells in with the sulfur pellets provided a very good media for denitrification. The other thing that was pointed out, though, that is a negative aspect is that we do get some sulfate production, and sulfate can cause a bitter taste in drinking water. The US EPA drinking water guideline for sulfate is 250 milligrams per liter. And so we do want to make sure that when we're treating wastewater using sulfur oxidizing denitrification, that we don't create a secondary pollution problem. The reason we focus on habits was, as most people are familiar with, these flow variations in the home. Everybody wakes up in the morning, takes showers, makes breakfast, does laundry, etc. In the afternoon, you might have people going to work and school, and then the evening get another high peak of wastewater load to the septic system. And we know that microorganisms don't like these high variations in flows and loads. During this morning and evening peaks, the nitrogen load can be too high for the microbial process. During the nighttime, the organisms might be starving. This is exacerbated when you have microorganisms that are or not microorganisms, but people in the household who are on vacation, who maybe it's a summer house where people are away 6-9 months of the year, and then they come back and the microbes have all died, and now you have to reestablish the microbial community. So the concept with habits is that we take advantage of ion exchange and biological treatment. So we use an adsorptive media. In this image here, we're showing zeolite as the adsorptive media. And zeolite is a natural mineral. It's mined in large mines out in the western states, I think in Utah and New Mexico. And the material that we used in this process was called clinoptilolite. And clinoptilolite has, in the lattice framework of the mineral, has sodium ions attached to it. When we bring zeolite in contact with wastewater, we get this exchange of cations. And so this cartoon here on the left panel is showing the black dots are the ammonium ions, and the red squares are the sodium ions. In the second panel of the cartoon, what we're seeing is that ion exchange process. Zeolite actually has a higher affinity for ammonium than sodium. So when we bring zeolite in contact with wastewater that has ammonium in it, the ammonium is adsorbed and the sodium is desorbed. Now, in the bioreactor, in the nitrifying biofilter, as the wastewater trickles through, it's bringing in oxygen, providing that electron acceptor for the nitrifying biofilm that's attached to the zeolite particle, and they start consuming that ammonia and converting it to nitrate. And what that does is it opens up that spot on the lattice of the zeolite for readsorption of the sodium. So in panel 4 here at the end of the process, we see all of the ammonium is converted to nitrate and the zeolite is bioregenerated. The important part about this process is that we didn't add any chemicals. The sodium was naturally present in the wastewater, and we also don't have to add any fresh zeolite to the system. At the end of the process, the zeolite is naturally bioregenerated, and it's ready to undergo the next cycle of adsorption and bioregeneration. So this is the results of just some adsorption isotherms. On the left panel, what you see is the aqueous ammonium concentration, and then on the vertical axis, we see the adsorbed ammonium. So this is basically showing that high selectivity of high capacity, and selectivity of zeolite to ammonium. And in this panel on the right-hand side, this is showing what's happening over time. And in this case, we see that the ammonium concentration goes down and the sodium concentration comes up during the adsorption cycle. This is some other work that we did with scrap tire chips. And interesting enough, we found that the scrap tire chips were a very good adsorbent for nitrate. So this is a similar graph as the one we saw with zeolite and ammonium, but now we're looking at nitrate concentration and adsorbed nitrate to the scrap tire chips. And you can see how we set up an experiment here with our little beakers containing our wastewater and our scrap tire chips in different masses of tire chips. So these are the materials that we added to our reactors. We had 2 stages, very similar to what Damon presented. The first stage was an unsaturated biofilter for nitrification. It included expanded clay as the biofilm carrier, the clinoptilolite, which is shown here, as the ion exchange material, and the oyster shells. Of course, we crush them, but this is just showing you what an oyster shell looks like for alkalinity. The second stage was a saturated biofilter for denitrification. It contained those elemental sulfur pellets. They look almost like lentils when you see them on the shelf. It had the tire chips for the ion exchange material, and also included those oyster shells. Another interesting thing about the tire chips was that we found that a little bit of the organic carbon from the tires leached out slowly over time from the tire chips. So in addition to sulfur oxidizing denitrification, we actually saw some of the denitrification was due to the organic carbon that was being leached from the tire chips. And that actually helped us to keep the sulfate levels low in our effluent. Here's some bench scale studies that we did. We had 2 reactors side by side. One was the Habits reactor containing the clay and the expanded clay and clinoptilolite, and the second was a control with just expanded clay. And what you can see here in the data, the orange dots are the influent concentration. The blue triangles are the effluent from the control, and the purple diamonds are the effluent from our Habits reactor. And what you can see is that right on day 1, as soon as we started feeding the reactor septic tank effluent, we saw very, very low effluent ammonia concentrations due to that ion exchange process. And we can also see that after about 15 days, our ion exchange capacity based on our calculations should have been exhausted. But what we see is that after that point, of course, the microorganisms are taking over and nitrifying our wastewater. In the control, on the other hand, there was this long acclimation phase before we got down to that low level of ammonia in the effluent. This is showing the denitrification experiment. What you can see here is a small column with the tire chips, the crushed oyster shells, and the elemental sulfur pellets. And we had nitrified wastewater coming in an upflow manner, and the denitrified effluent. This is showing the data a little differently. What we show here is the flow rate times the influent nitrate concentration, showing these diurnal variations in load. So we had a high influent variability in the nitrogen load, but despite this high variability in the influent nitrogen load, we still had very low, stable nitrate concentrations in the effluent. So we were very happy with this proof of concept. So then we, working with our partners in Hillsborough County Advanced Wastewater Treatment Plant, we built a pilot. We had a septic tank, an aerobic biofilter, and an anoxic biofilter. We actually ran 2 systems side by side, one which we called R here, which had recirculation and pre-denitrification, and the other one we called FF for forward flow, had no recirculation. And again, similar to our previous experiments, we used this diurnal influent load where we had high loads in the morning and evening, a low load in the afternoon, and the system shut down in the evening, at night. This is just a schematic of the system showing the septic tank, the pump, the stage 1, stage 2, and then in gray with the dashed lines, it's showing the systems that were on for the in place for the system with the recirculation. Here's some results from our pilot system. What you can see here now in orange dots, we have our high influent ammonia concentration. And then we can see the purple is from our system, our forward flow system with no recirculation. Both of these had cleanup till light, but they were both habits processes. The difference was with or without recirculation. We found that recirculation improved performance. This is just a snapshot showing the nitrogen speciation. You can see the influent, which is mainly ammonia and some organic nitrogen. After stage 1, much of that ammonia is being converted to nitrate. And then after stage 2, almost all the nitrate is gone. In fact, throughout our experiments, we had extremely good performance of stage 2. The system that had the tire chips and the sulfur pellets consistently had nitrate and nitrite concentrations below our method detection limits. And this is just showing the performance with a 1-to-1 recirculation rate or a 3-to-1 recirculation rate. And we actually didn't see any difference in performance between those two recirculation rates, no statistical difference. And this is showing, again, that variability in the influent load, showing the morning, the afternoon, and the evening, and that very, very low, steady effluent concentration due to the combination of the ion exchange and the biological processes. So if you want more information about this, we published a paper that was recently published in the Journal of Sustainable Water in the Built Environment. And I just wanted to give a shout out because it was part of a special collection on Onsite and decentralized wastewater management system. And I have the link here. And I know there's a few other authors on this call, I noticed, who have published papers as part of that special collection. So now I'll pass it on to Jim.
Okay. Hello, everybody. And just to let you know, we're close. I only have 3 or 4 slides here and a couple minutes of comments. So, we'll move on to the next slide. But really, the issue is why develop a university utility partnership? And from this nice quote, I think the key here is universities that are local to utilities, we can assist with developing site-specific solutions to technical problems. And, this is definitely something built around synergistic benefits in terms of technical problem solving and also training future professionals for the utility. And I saw a question on implementing in developing countries. There was an IWA AESP workshop, I think about 2 years ago, and there was also successful partnerships highlighted between university and local community partnerships and U.S. universities and international universities. Next slide. So in terms of if you're not familiar with these types of partnerships or you have one and you want to improve it, I first make the point, we did not invent or were the first people to recognize the importance of such partnerships. We just happen to be one of several successful partnerships around the country. And if you're interested in setting up a partnership or enhancing an existing partnership, there's a lot of good material available for the public on the web. So there's a 2017 document from WEF. There's a 2019 document from AWWA, NACWA. There was recently a March special issue in Water Environment Research about successful partnerships, and then we also had a publication in Environmental Science and Technology devoted to this project. And I'd even say internationally, IWA has been a big supporter of these endeavors. So lots of good materials here on how to develop a partnership or how to enhance an existing one. And I should point out these documents, they provide evidence why this makes good business sense to utilities. So for people that are interested in getting information on how to make the business case for these partnerships. And these documents also talk a lot about supporting training of early career professionals. The next slide. So the document we provided on the previous slide, it provides a list of partnership benefits, general characteristics of successful partnerships. And so I would say unique to our partnership between the University of South Florida and Hillsborough County is the county is very interested in optimizing current treatment processes, but they also want to identify future processes so they can achieve better environmental sustainability. And our partnership also has a goal of leading to incorporating an advanced technology, educating customers and the public about local resource recovery facility that is in our area, and then also educating K-12 and university students in environmental science, technology, engineering, and math skills. And then we always wanted to educate and mentor students for staff succession planning. The county staff serves on thesis and dissertation committees. They've also co-authored publications with our students. And then we also recognize the importance of expanding the partnership. So, for example, Damon Anderson from Hazen and Sawyer is part of our team, and we have expanded that partnership from utility university to the consulting community. And obviously they have technical expertise, but also expertise in estimating cost and making business cases. Okay, on the next slide, so a successful partnership is more than one individual, and so I think there's a lot of examples of a partnership with one professor and one utility partner. And so some unique aspects of our partnership is we have a utility PE and a university PI that are the people that develop and execute the project. They coordinate documents and all these activities. Our main focus is to support the operational division, as I had alluded to before. But within the county, the engineering planning, the regulatory, and the laboratory service groups all provide expertise and data that's required for work that we do. And then I would say another thing, when we developed our memorandum of cooperation between the university and county, it was written such that other county departments, such as public works, can be involved. So the partnership is also used not just on this wastewater example that we're talking about, but partnerships for stormwater, wetland, and pond surveys. So that's what I wanted to say about university partnerships. Serena, I'll hand it over to you now to conclude the talk, and then we'll move on to questions.
Okay, so as Damon mentioned, on-site wastewater treatment systems can be a significant source of nutrients in many areas. It's often in low-density housing areas, not cost-effective to convey wastewater to centralized systems, and they are very, very highly used in developing countries. Passive on-site wastewater treatment systems can provide effective on-site nutrient removal with low complexity, low O&M, and energy and chemical requirements. In our research with zeolite, or the material clinoptilolite, and the scrap tire chips, we found that the ion exchange material could serve as a buffer that provided consistent low effluent nitrogen concentrations despite highly variable loading rates and long idle periods. I didn't mention, but we did experience a hurricane during our study, and we had to shut the system down. So we had a kind of an enforced idle period and then went back, and that's discussed in the paper in detail. We're doing ongoing research on the performance. We have, I saw Michelle Henderson on this call. She's doing some work on life cycle assessment, as well as looking at reuse potential. We have another student looking at some modeling of the process. And as Jim mentioned, university utility partnerships have synergistic benefits, resulting in a win-win for both partners. So these are some of the graduate students, postdocs, the RUs and RETs. We had some local high school teachers who helped us out on this project, and other USF faculty, Maya Trotz and Kabrab Gaber-Michael. And here's some of the funding agencies and partners. And then I put our email addresses on the final slides in case you want to contact us afterwards.
Okay.
Great. Thank you so much, guys. Now we're going to open it up to question and answer. For all the attendees, if you have a question, you can click on attendee chat in the left-hand corner of your screen, and you can type in your question there. The three speakers will go through the questions and answer as best they can. We have a huge audience today, so any questions that don't get answered, please feel free to email them. And okay, we can get started.
All right, Marissa, this is Damon. I'm going to field the questions and then put them to whoever can answer them best, because I have them listed here on my computer. So I'm just going to go through them in the order that they came in. There's a lot of questions, and I don't think we're going to get through them all, but we're going to try. So first one here is, what do you do with the effluent during the rainy seasons? And I'll take that one. The systems we put in are similar to a typical on-site system. So the effluent still gets discharged, rain or shine. That the one we use for reuse, it still goes to the irrigation system. Keep in mind that the flow from the on-site system is very, very small volume-wise compared to precipitation. So, you might have 150, 200 gallons a day going out from the on-site nitrogen reduction system, whereas a half inch of rain could be, several thousand gallons over the yard. So it's not a big problem, and they discharge just like a conventional septic system would discharge, rain or shine. Next question is, you compute a predicted sulfur consumption from the stoichiometry. There's two sulfur questions here. I'm going to take a crack at it and then turn it over to Serena. But yes, we did look at the sulfur stoichiometry, and the sulfur consumption follows the stoichiometry relatively closely, but there's a 10 to 20%, I would say, excess consumption due to oxygen getting into the system primarily. So if you can't keep oxygen out completely, which in the field is a little bit harder to do, you might get 15% more sulfur consumption than you would if you could completely eliminate oxygen. So that's the question there. But otherwise, the curve follows stoichiometry pretty well. Next question is, the sulfur.
Yeah, let me also bring in our experience with that, because we had only a small amount of sulfur in a media that was mainly a tire chip matrix. And so we found that we were below the stoichiometric. I can't remember exactly off the top of my head, but I want to say about 70 or so % of what the stoichiometric amount of sulfate production would be. And we've also done some work where we've combined sulfur and wood chips as well, and we've come out below the stoichiometric sulfate production.
All right, good. Next one's also a sulfur question. Does sulfur cause a groundwater sulfate issue? Answer there is it can. One of the key reasons we looked at using the wood heterotrophic denite first prior to the sulfate was because of that issue. We tried to knock down the nitrate as much as we could with the wood denitrification prior to going to the sulfur to reduce the amount of sulfate produced. And we did not exceed really, in most cases, the groundwater or the secondary Safe Drinking Water Act sulfate concentration, but it would add to groundwater sulfate from these systems that discharge to the soil. But you can control that somewhat. In coastal areas, of course, it might not matter as much because seawater around Florida is very, very high in sulfate. Anything to add there, Serena?
No, just the same comment where, definitely there's some strategies for getting that sulfate concentration down.
Right. Next question is, what are the characteristics of the sand? I mean, we typically used sand very similar to what would be used to construct a septic system drain field or a mound system. In a lot of places, they're using more engineered sand, more sieved or produced sand, such as DOT road sand and what have you. Like I think in Long Island and Cape Cod, they're using more of that. But really, a conventional on-site system in Florida, which is mostly sandy soils, does great nitrification in the sand. So it's the specifications I think are in our code, but it's not very strict. What is the outlook for implementing such a system in developing countries? Next question, and I think Jim addressed that. But Jim, you want to say anything more about that?
Yeah, I would just say if you look at an on-site system in a developing country, a lot of times it's a latrine pit or it's a disposal pit. So the septic tank is not usually associated with the drain field. So I think there's a good outlook. There's research looking at lining latrine pits, for example, or lining underground disposal pit with locally made materials like we're doing to try to reduce the transport of microorganisms and also reduce the ammonia nitrate loading into shallow groundwater. So I think the idea is to take some of the fundamentals processes that are used here, physchem and microbiological, and apply them to a latrine pit or an underground disposal pit.
Yeah, also, as Damon showed, he hit their work. They had very low numbers in terms of fecal indicator bacteria. We also saw in our systems, we had very good removal of fecal indicator bacteria. And we followed our system with a chlorine tablet feeder, looking at trying to, disinfect the effluent for more on-site reuse applications.
Okay, very good. Next question. How does the system handle fluctuations in water quality and quantity? And is the system scalable? I'll address our systems first. The simple systems, in-ground systems we developed, they handle fluctuations in water quality and quantity very well. I mean, just like a conventional on-site system does, but produce better treatment in the end. And of course, we took our pilot and prototype works and we scaled it up to full-scale individual homes. You could scale it up further, I believe. We haven't done that yet, but I think that would be possible. Serena, you should probably address those same questions for your stuff. Fluctuations in water quality and quantity, which you guys addressed, and then scalability.
Yeah, we, our system, the pilot system, was still smaller than a single family household system. So even though it was a pilot, it wasn't a large full scale system. So I'd say Damon has much more experience with that in terms of the fluctuations in water quality and quantity. We found that the ion exchange media was very effective. We ran the side-by-side systems with and without the ion exchange media, both stage 1 and stage 2. I didn't show you all the data from that, but we found that we had significantly better performance with the ion exchange media than the control without the ion exchange material.
All right, good. Another one for you, Serena. How many reactors does it take to operate a HABITS system?
Well, it's just the same as the what Damon showed. You could do it as an in-ground system, but you know, you need to have one aerobic stage and one anoxic stage. The main difference is that, you know, in the aerobic stage, what you're trying to do is nitrify. So you want an ion exchange material that has a good adsorption capacity for ammonium, which is why we use the clinoptilolite. In the denitrification stage, you want to have it saturated, so it's waterlogged, it doesn't get much oxygen transfer, and you have an ion exchange material like the scrap tire chips that have a good ion exchange capacity for nitrate.
Okay, next question. What is the projected, and there's actually 3 or 4 questions here. I'll go through them one at a time. What's the projected lifespan of the bioreactor media? Of course, the nitrification media, it's got a very long lifespan. It's simply inert, and all it does is cause an unsaturated environment for nitrification. The biomat lives on the media, so that's not really an issue. The reactive media, either the sulfur or the wood. Sulfur, you can predict relatively closely with stoichiometry. It's either a little more or a little less, like we answered before. The wood is a whole other question. It's very difficult right now. We don't have any equations or any lifespan way to figure out lifespan of wood. Every batch of wood seems to be a little different. Of course, it's not a uniform media, so that's difficult, but I can tell you that they last a long time. I mean, there's just the best case I can come up with is a denitrification wall that was put in by the University of Waterloo up in Ontario. And that system is still removing nitrate after, I think, over 25 years of operation. But it's removing nitrate from groundwater, a little bit lower concentration. But again, they did a sawdust sand mixture wall. Groundwater flows through it. That system's been removing nitrate for, like I said, over 25 years. Carried another question within that one. What are other issues are associated with these designs in terms of O&M and rehabilitation, replacement? Well, of course, it's going to be more expensive to design a little bit. O&M is not too much more for these in-ground systems. Tank-based systems with recycle and all that might be a little bit more O&M. And then rehabilitation replacement, you're going to have to replace or add to the reactive media for denitrification over some length of time. And that's, of course, going to depend on how big your initial reactor is and what the volume of media you have in it. But the cost compared to conventional systems, part of that same question. It's going to cost a little bit more than a conventional system, but I don't think it's going to be, it might be, yes, it's hard to say. It's going to really depend on the system, but it maybe double the cost of a conventional. We were able to do one of these in-ground systems for like $12,000 to $15,000 in Florida, and I hear now there might be some going in for even less. But that gives you a rough ballpark. Installer expertise, installers, septic system contractors do have to be trained to do this because they're not difficult, but there's some things you got to do right to make sure these things work. And so that there's training that's going to be needed for that. Long questions there. Next one, how many have been installed in Florida? How many total in the USA? I don't know the answer to that. Maybe somebody from DOH. I see Dr. Gao is on, maybe Eberhard as well. I think last list I saw, there may have been more than 30 so far installed in Florida, over and above the ones we did as part of the 7 we did as part of our project. I'm guessing maybe somewhere up towards 50, but I can't document that. Maybe we'll get an answer come in. How many?
Cape Cod has had a big program on this as well, so that may be another place where there's a fair number of these that have been installed for a while.
Yeah, and I know there's George Hoyfelter's on the line. He's installing some in Cape Cod. I know.
Okay, here's George, 15 in Cape Cod, there, right on cue.
And I know Chinwei is on from Stony Brook, and okay, so he says about 200. Anyway, there's a lot of them going in. I think every day it's increasing, and so I can't tell you an exact answer, but it's not just a couple of them. Okay. Next question. Could you elaborate why it's not suitable for conveying wastewater to centralized system in developing countries? I'll let Jim answer that, but I think it's because there are, well, in many places, there's not a centralized system.
Yeah, so most of the unmet need for improved sanitation in a developing country is in a rural area, right? And a lot of rural areas in developing countries are very spread out, like a lot of city planning is done here in the U.S. And then the second thing is the other need for improved sanitation in a developing world context is in what I would call urban areas, but they're peri-urban, so there's these unplanned settlements, and so that creates some issues with putting the cost and the logistics of putting in a collection system.
Right, and while the examples that Damon gave were for a single household system, there would be a small community or a cluster of houses could also implement this type of an approach.
Yeah, that's correct. Okay, here's a long one. I'm just going to kind of paraphrase some of this, but it says research on ammonia removal by ion exchange using clinoptilate has been looked at University of Michigan in the 70s. I'll add that we looked at it at University of Wisconsin in the 70s too when I was there in grad school. And there was several PhD and master degrees are published on the subject matter at Wisconsin as well. Here's the main question for probably Serena. One key parameter that was not discussed in this presentation is the hydrodynamics of the system that has important impact on the system performance, primarily the external mass transfer for ammonia in the bulk fluid to the pore of the exchange media, and also the control of biofilm thickness, so it does not become a serious limiting factor in the system performance. And I know that some of that was experienced in those early 70s work, but Serena, what's your response there?
Yeah, our experience is similar, and when we look at the recirculation, the system definitely performed better with recirculation than without. The recirculation, we know, improves the mass transfer of the substrate to the biofilm. It also improves the oxygen transfer into the system. It also plays a role, and we saw that very dramatically when we did do a backwashing of the system. We had a lot of clogging in the system without the recirculation. With recirculation, we had very, very low VSS levels in our backwash water. So we found that the recirculation played a major role in maintaining those nice thin biofilms that were highly active and could get good nitrification rates. On the other hand, if you have too much of a hydraulic load in the system, you can get ponding, and that can inhibit gas transfer. And so you have to be careful not to apply so much recirculation that you have too much of a hydraulic load to the system. And I think, Damon, you had some experience as well with problems with hydraulic loading, right?
Yeah. I mean, the hydraulic loading, it has to be low enough so that you don't get excessive biomat at the nitrification layer. That's the most critical spot. We haven't had many problems with the denite, but the nitrification, if it's loaded too highly, will form a biomat that will restrict flow. So that's a critical factor. But we have found, and this relates to the next question, what's the footprint of the system for a typical family of 4 household? We found that sizing them roughly equivalent to what a normal on-site system drain field would be sized for the given soil is okay for the sizing of these systems in ground, at least. So again, if it's a sandy soil, certain kind of fine sand soil in Florida, it might be 0.75 gallons per acre square foot. Other states have maybe different numbers, but that's what affects the footprint size of the top layer. In terms of the tank systems, Serena, maybe you have an answer for that, what your loading rate was. I mean, we loaded ours at like 3 gallons per acre square foot, and that worked.
I think we followed your advice on that. Josephine was working with us in terms of the hydraulic load, so we followed your based on your experience.
Right. Now, the 3 gallons per day per square foot for our tank systems, which are similar to what Serena showed, that was for an engineered media. We use a very coarse, clean filter sand for that. So not a normal soil, not a normal natural soil, but a filter sand. And we were able to achieve 3 gallons per day per square foot, I think with recycle that was. So anyway, that's that. Let's see here. Here's one for you, Serena. Would the scrap tire chips present any potential concerns with PAHs?
So we did review the literature on the toxicity studies. FDOH actually had gave us a lot of good information on studies that had been done when they approved the scrap tire chips as a drain field material, and so they had already looked into this issue. Now, there is a fair amount of literature on tire rubber, but showing that it is toxic. But in that case, what they were looking at is the actual material that is, removed from the tread of the tire when the vehicle is operated on the roadway. So of course it's picking up a lot of oil and grease, and it's a very fine particle size. And that material has definitely been shown to be a toxic material. But these scrap tire chips, at least we didn't do any toxicity studies in my lab. We did some metal leaching studies, but we felt pretty confident that they weren't going to introduce any problem, especially given the diligence that FDOH had done on when they approved them as a drainage media.
Okay. Next question, cost installed. I think I hinted at that. I think we're seeing costs. It's going to depend again on the size of the home, the size of the system, the location of the system. So there's a lot of variability, but I think you could figure somewhere 15 to 20,000 for one of these installed systems here in Florida, in-ground systems, that is. I know they're much more in the Northeast, probably at least 10,000 more than that. But again, it's going to vary quite a bit depending on the site. Again, what's the expected life of the media? Already addressed that one. And I think it's going to depend on the size, but you could design these things, I think, for 20 years if you wanted to. With a tank-based system, you could always add media, so it's not as big a deal. But the in-ground, you want to size it large enough to last quite a while. Next question, for media containing wood chips, is there a risk of fouling from fungal growth? No, we haven't seen that, and we try to make sure that the wood chip area is anaerobic or anoxic, at least in the liner, and saturated. So we don't usually see any fungal growth there. Maybe at the interface you might see some, but it hasn't been a big problem.
Yeah, I have a couple of buckets of wood chips in my lab that are submerged. We're kind of doing this long-term experiment with them. When you put wood chips out on your yard, they under aerobic conditions, the next year, what happened to all the wood chips, so they break down fairly quickly under aerobic conditions, but under, submerged conditions, they as Damon mentioned with the University of Waterloo studies, they really have been shown to last a long time.
Okay, a lot of questions on cost. The Department of Health here in Florida might be able to give better numbers on cost now that they've got quite a few in, but I've given the numbers that I think I would have access to. Any effects on P concentration, phosphorus concentration? We saw a reduction in phosphorus, but it wasn't what we were designing for, and it wasn't that significant. Serena, you guys may have seen more.
No, we didn't see much reduction in phosphorus in our system. So we would probably want to, do some type of a downstream adsorption process, or, if phosphorus removal was an issue.
Yeah, it's not a big issue here in Florida, so we didn't look at it. We have relatively high natural phosphorus, and phosphorus doesn't seem to travel far from on-site wastewater system drain fields. The soil does a pretty good job in attenuating phosphorus compared to nitrate. Is there a design guide that discusses loading rates to the various filter stages? Any information on BOD removal with the systems? You know, go on the DOH website to that slide. And Marissa, I'm sure the slides are going to be available, correct?
Yes, they will be available online by the end of the week.
Okay, good.
Yeah,
And
hard to go back.
yeah, don't worry about it. There's a on the slide, several of the slides, there's references that you can go to find out more detailed information. We did a detailed report for DOH on this test systems we did that talk about the loading rates and the stages. BOD removal gives all the data. So
yeah, I thought you had BOD numbers here, but you don't. Yeah,
no, I don't have, you know, through the sand. First stage sand, the nitrification part, the BOD is like negligible. You can't measure it, but then you gain a little bit of BOD from the wood that is then potentially utilized through the sulfur. And if you don't have sulfur, it goes to the drain field. But again, it's very low compared to septic tank effluent. So the drain field will handle any residual BOD that comes off. I mean, we never saw BOD numbers greater than 30 or 40, I don't think. In our test systems, which any drain field could handle because they're designed to handle more than that.
We mainly measured COD and we had very good COD removal. I do want to mention, though, we had a little bit of a problem with stage 2 where we had some turbidity in the effluent, so that you do get, and I don't know if you saw this, Damon, you get some sulfur particles that are carried out of the reactor, and you get a little bit of a cloudiness, yellow cloudiness in the effluent. And we found that did interfere with the chlorine disinfection. And so we actually got much better results in terms of fecal coliform removal when we looked at just stage 1 treatment followed by disinfection. So we actually took all stage 2 off completely and just put in the disinfection stage, and we got very good BOD removal, nitrification, some denitrification because of the recirculation, and then disinfection using the chlorine tablet feeder. So that was one of the recommendation for on-site reuse.
Yeah, and I saw the same cloudiness after the sulfur, not after the wood so much, but after the sulfur, we did see a little bit of a cloud, kind of a yellowish, milky cloudiness, but it didn't impact the nitrogen concentration, but it would probably impact disinfection. Now, most systems in Florida are going to go to a subsurface drain field disposal of some sort anyway, and so the disinfection we wouldn't really use it in most cases, and not being used in most of the cases we're putting them in now. Here's a comment about peat fiber being used for 30 years, and it works as well. It works well as also. Just a comment. Oh, here's Serena. Do you think tire chips would absorb nitrate even in aerobic environments, like for stormwater?
Even in aerobic environments. Now, I know that there is some work that's been done by University of Central Florida. They have a media that they call, I think, brown and gold, or I can't remember. It's 2 colors, gold and gold. Yeah, and it's a mixture of the tire chips and wood chips, and they've done some extensive work with looking at treatment of stormwater. So I would definitely refer you to some of their work where they've looked at using it under sod in different golf courses and things like that. So they've looked at that material in a lot of different environments.
Yeah, and I saw Marty One Listed was on the call earlier. I don't know if he still is, but Marty One Listed is the guy to talk to over at University of Central Florida. He runs the Stormwater Academy, and they've been doing a lot of work with that. Okay, here we go. George Hoyvelder again says 15 of salt in Cape Cod. Dr. Gao at DOH says about as of the end of April, about 200 in-ground systems installed in Florida. So that's even more than I thought. I know there's quite a few going in. Is there any reason this technology could not be used for community soil systems? Yes, they could. I think it could scale up. Obviously, you need land area like you would for any kind of land treatment system, but you certainly, I think, could scale these up for cluster or small community application. Oh yeah, George. George Horfeller's got a great comment coming from up there in Cape Cod. You should mention that the temperature impacts the denitrification. That's exactly right. We don't have that problem in Florida, but George has seen impacts below 10 degrees C. He sees significant nitrate breakthrough. Okay. Is engineering design needed? For the in-ground systems, I think Florida's got in their code kind of a prescription design, and they're not requiring engineers for that system. Other places they do, and if we go to tank-based systems, it will probably be, actually, I might be wrong about that. Dr. Gao, if I'm wrong about that, just send me a quick note. Maybe you're requiring engineers. I can't remember now. But anyway, not for all states, but not for all systems. Dr. Rubin, a consequence of nitrate conversion to N2 results in an increase in the electron donor. Please discuss relative risk of increase in SO4 or organic carbon relative to the reduction in NO3 concentration.
Say that again.
The relative risk of the increase in SO4 or organic carbon, in other words, the SO4 from the sulfur or the organic carbon from the wood, the relative risk there relative to the risk for NO3, I think is what Bob is saying.
So I'm not sure if you're talking about sulfate reduction. We have seen some sulfate reduction in our bioreactors, particularly when we were, I did some research in Cape Cod actually with George when I was at the University of Massachusetts Amherst, where we had the reactors that were full of sulfur. We saw that we got some sulfide production in our reactors. This could have been due to the organic carbon as the electron donor and the sulfate as the electron acceptor, and you get some sulfide, which it can be toxic. You can also see a microbial process called sulfur disproportionation, which also generates sulfide. So you're right. I think that might be what you were getting at, Bob. You do have potential for odors. You can due to sulfide, as well as sulfide can be toxic itself. So that is a concern, and another reason why using in the mix of wood chips and sulfur, or tire chips and sulfur rather than 100% sulfur, I think is a good approach.
Very good. We're coming down to the end of the questions here. Here's one. If there is a really high-end crop that can be grown safely on the effluent in everyone's backyard, would denitrification be needed? I'll let you guys respond to it. My response would be, well, I think that is good for reuse, but you still may have a nitrate problem. So I don't know if that would handle all the nitrogen produced, but it could certainly help. And obviously, if you do reuse like we did irrigation, plants are going to take up some of the nitrogen, but we still see some nitrate coming through from some of these systems. Serena, anything to add there?
Just currently, one of my students, Michelle, who's actually on the call, I saw is doing a life cycle assessment where she's comparing the conventional approach of on-site wastewater treatment and potable water for irrigation with the habits process and on-site reuse for irrigation. So hopefully we'll have the final results from that study soon.
All right, good. Comment back from Dr. Gao at Florida Department of Health. He's responding to my question. The current rule for in-ground nitrogen reduction biofilters will not need an engineered design as long as the drain field does not exceed 1,500 square feet. So that would take care of most single-family homes, but for something bigger, you would probably have to go to an engineering design. So thank you, Dr. Gao, that was good. That's the last of the questions. So thank you all for attending. I can't believe the response to this. It's been very great, and I'm glad there's so much interest.
Yeah, thank you very much. I think we benefited
Thank
from
you
the
so much,
pandemic.
everyone.
Yeah,
Thank you so much,
everybody.
everyone. Everyone really enjoyed it. Like I said, the slides and the recorded presentation will be up online later this week. And if you have any questions, please feel free to email myself or the three speakers. The email address is on the last slide there. And everyone have a great day. Thank you so much for attending.
Thank you all.
Bye. Thank you all.
Thank you. Bye-bye.
Yeah, goodbye. Stay safe.